And part of the reason it's vulnerable is because 100% of its watershed is being treated. And we think for a vulnerable risk assessment, that's a reasonable thing for eco-risk. When we started doing drinking water, and we started doing drinking water estimates about 1999, we didn't feel that that kind of a scenario was reasonable because no drinking water facility has just 10 hectares for its watershed. So we developed a bigger water body. I'll talk a little bit more in a second. That's 178 hectares. That's a 5.3 hectare reservoir with a mean depth of 2.3 meters. It does have flow through it. And a real critical point, when you get up to this size, 178 hectares, it's no longer reasonable to assume it's all going to be planted to one crop. So we apply a PCA factor, which is percent crop area, to account for it's basically the maximum amount of that crop that's found in any basin in the United States, any drinking water basin. This is kind of a pictorial representation of our standard pond. And that is the actual real index reservoir. The index reservoir is based on a real lake. And the reason we picked it is because, partly because we knew it was vulnerable. We knew it was vulnerable based on monitoring data that had been collected. I can even tell you it is about a 90% site. About 10% of the drinking water sites where atrazine is used have higher concentrations. About 90% have lower concentrations than Shipman City Lake. The highest sites have concentrations that are about twice what you'd found in Shipman City Lake. But again, it's only about 10% of the sites. I will also add that all the sites that we looked at for this were from a collection that came from the Midwest. I think we've learned since that drinking water facilities in the Midwest as a group tend to be more vulnerable than they do on a national basis. So there may be a little bias on that account. But in fact, we were able to show, before we started to use it, that the concentrations we were seeing from modeling were about the same as the concentrations we were seeing in the monitoring data for Shipman City Lake. So we were pretty confident that it was a reasonable representation of a vulnerable but not a worst case site. Now, that's the real Shipman City Lake. This is what it gets turned into when we put it in PRISM exams. There's an abstraction process that goes on. You get a generalized watershed of a certain size. There is a stream that flows into it, and it is a perennial stream, and we factored that in. We considered the spray drift that can go into the stream, and the spray drift that could go into the reservoir. And this is kind of how it would look when it gets put into exams. So it's also useful to remember that even when we're looking at a real environment, when you start doing models, there's always a process of data reduction that goes into turning whatever you're putting into a model into that model. So I want to talk specifically, up until 2 or 3 years ago, we only were able to do agricultural scenarios. We wanted to start doing turf. So we had a couple of issues to deal with. One, we needed a turf scenario specific to turf. And then we needed to worry about some things with the residential and the impervious surface. So the turf scenario, and we've got 5 of them now, 2 in California, 2 in Texas, and 1 in Florida. And the one in Florida is kind of the one you go to first because that's your kind of 90% site. The 2 in Texas and 2 in California have been set up for endangered species assessment for it because there are particular endangered species involved. How did we adjust these from the agricultural scenario? And Stuart made an allusion to it. We added a turf layer. We added additional soil horizon, but we're using that soil horizon to reflect that thatch layer that's on top of the soil. It has a higher organic carbon content and a higher water storage capacity and an increased ability to hold on to strongly bound pesticides. The other thing we had to do is change the curve numbers. And why there's 2 in California and 2 in Texas, there's turf, like for sod production, and there's one set of curve numbers for that. In that case, the curve number would go down because when location just has turf on the top of it, you tend to get a reduction in the amount of runoff that can come off it. The turf and the thatch, to some extent, act like a sponge. For residential, you'll actually get an increase coming off the turf, and we use a higher curve number. A curve number is basically, I should say, is a parameter that's used in modeling that basically determines the ratio between what infiltrates and what runs off. And it's higher for the residential scenarios because of the impervious surface, the roofs, the driveways, that generates water that runs across the turf. This isn't the impervious surface itself and its runoff. It's that it generates, the impervious surfaces, like the roof, generates some runoff, and then it has to go to the across the turf before it gets to the driveway, before it gets to the storm drain. So you have to increase that because there is some additional delivery because of that run across. When we start talking about residential scenarios, and I was interested to see, I've seen several of these today, where the same kind of idea. This was done specifically for California, and in California, or at least Northern California, a quarter-acre lot is typical, and houses have typically a footprint of about 1,000 square feet. So if you take your quarter-acre lot and you subtract out 1,000 square feet for the house, and you also subtract out a driveway that goes to the house and is about 15 feet wide. I got 15 feet wide because I measured my own driveway. You leave 9,345 square feet for a lawn. Then we've got the overspray zones, and I have a 3-foot wide swath of overspray around the edge of the lot on the road, overspraying the driveway, and overspraying the sidewalk. So each of those is a 3-foot wide swath. And for corner lots, you'd have it on 2 edges, and if it's a lot that's in the middle of a lot, or in the middle of a block, it would just be on one side. The question is, how many houses do I fit? We've got this 10-hectare watershed for eco-risk. And the last piece of information we got for some GIS was that in Central California, typically about 50% of the lots are lawn and 50% is impervious surface. And that impervious surface includes the driveway, includes the house, but also includes all the roads. So we wanted to figure out what was left over. Did the calculations, and I found out I could get 58 quarter-acre lots into that kind of a watershed. Okay, so considering that, the 58 lots with the overspray zones I got, I was able to estimate that 1.68% of the impervious surface would be oversprayed in a residential watershed. So when we're doing residential